Okay, let's look at light as light crosses through a boundary. Now, if I've got a particular medium light can travel through, we need a way of talking about that medium. What we're going to do is we're going to define that medium in terms of what's called the index of refraction. Now, the index of refraction is defined by c, the speed of light in a vacuum, which is close enough to 3.0, which is 3.00 times 10 to the 8th meters per second. We know that more accurately. I think it's 299,798.56. 299,758,000. It's to 3 sig figs, 3 times 10 to the 8th meters per second, divided by the speed of light as it goes through that particular medium. Now, light will be traveling at its fastest through empty space. And so other cases like, say, water, glass, those will have, when light is traveling through those materials, it will be going more slowly. Such that we have a list of things like, for example, the index of refraction of, let's see how much space I've got. The index of refraction of a vacuum is defined as 1.00. It's because the speed of light in a vacuum is equal to c, so c over c, that is 1. Now, the index of refraction in air is 1.00, I believe there's another 0, yes, 3, which is close enough to 1, especially if we're just working with 3 significant figures, that we can say, oh great, let's just call that 1. Let's see, typically, the index of refraction of water is 1.33, and the index of refraction of glass varies depending on the type of glass that you have. You can go through and find companies who specialize in making different types of glass with different indices of refraction, and that behave differently throughout the spectrum for the purpose of making, like, special types of lenses. A common value for glass, it tends to range from about 1.4 to about 1.7. So let's say 1.5. Notice that this index of refraction is the ratio of one speed to another speed. So there are no units. Now, since I'm defining a particular medium, if light can travel through that medium, I'll define it in terms of its index of refraction. If I want to look at how light, interacts as it goes from one medium to another, curses. Okay. We have light coming in to where it crosses from one medium to another at some angle of incidence as we used before. Now, find out what happens if I have some other point in the second medium that I'm defining. It's like, oh, how does the light get from point A to point B? As before, the light takes the path that gets us there in the shortest time. Now, if you're just staying in one medium, that's a straight line. But if you're going from a material in which light is moving at one speed and going into a material where it's moving at a different speed, then you probably are going to have like, well, it serves you well to have a longer path in the material in which light can go faster, and a shorter path in the material where the light slowed down. Happily, this breaks down to a really easy relation where the index of refraction of material 1 times the sine of the angle of incidence is equal to the index of refraction of the second material times the sine of the angle of refraction. This is known as Snell's law. And it's actually, quite a straightforward relationship. Now, in this case, this is bending inward. This is what it will look like if the light is traveling from some material that's got a low index of refraction into a material that's got a higher index of refraction. It's going to bend toward the side. What's cool about this is that notice that this angle doesn't have any directional information. If I have something that starts here, then the path that light would take going in the other direction would be exactly the same. It'd go right back along that path as it's going from a high index of refraction to a low index of refraction. It would appear to be moved outward away from the normal, which brings us to an interesting point. Let's say that I've got some object, again, such that the index of refraction in 2 is greater than the index of refraction of this material in 1. Now, if I have a ray of light that goes straight to the intersection, or the shortest possible path to the break between the two mediums. So here, the angle of incidence is 0. The sine of 0 is 0. So that means that n2 times the sine of refraction is 0, which means that the sine of refraction has to be 0, which means that theta has to be 0. So if you have light, like if you take this with a pane of glass, you take that glass and you're looking directly through it, it's not distorting the path of the light. Hey, that's why you have like a nice flat window, everything still looks lovely. There's the outside. If I've got a ray of light that hits off of the normal, then the resulting path is going to be bent farther away from the normal than it had been in the first medium, the medium into that it started in. So the farther away I get, the greater this angle gets. So that means there should come a point where the angle of refraction is equal to 90 degrees. because as this angle, as the refracted light gets bent farther and farther from its original path, eventually it's going to hit a point where, hey, it's at 90 degrees. Now, that is known as the critical angle, such that, okay, n1 times the sine of the critical angle is equal to n2 times the sine of 90 degrees, or n1 times the sine of the critical angle. Since the sine of 90 degrees is 1, that's just equal to n2, or that critical angle between material 1 and material 2 depends upon those two, as I had written this, it's starting in N2. So to keep it the same as this diagram here, it's starting in N2. And notice that this only works if this object, if the material, the medium that it's starting in, has a higher index of refraction than the medium it's going to. Because this number then will have to be larger than that number. So N1 over N2 will have to be less than 1, which is the only way that this answer will make sense. If you try and find the arc sine of 1.7, your calculator is going to look at you, look, you've gone crazy. Now, let me clear a bit of this space. Actually, let's say that I've got